next speaker. Our next speaker is Jonathan Selinger from Kent State University. So we are waiting for him to connect. If there is any questions for him, we can use this time as well.
Yes, hello, do you hear me?
Hello, hello, Jonathan.
Hello, okay, let me get this presentation up here and I'll do the sharing.
Okay, the Zoom is yours.
Thank you. Share, PowerPoint. All right, do you see my PowerPoint now?
Yes, we can see it.
You see it, excellent. Well, thank you, Madam Chair. Thanks to all of the organizers. I am so happy to be here in Slovenia. Let me begin here. Okay, so in this talk, I want to present a whole ideology for how to think about modulated phases in liquid crystals. Okay, this ideology has several steps. To begin, the first step is to classify the director deformations that are possible. Okay, so this was my talk at the last FLC conference in Boulder. As you might or might not recall from that, there's a system for classifying director deformations, which is based on what's the symmetry of the deformation under rotations about the local director. And so it breaks the director deformations into 4 normal modes, which are different types of mathematical objects. The first normal mode is bend, as you see here. This object is a vector in the plane perpendicular to the local director. The second is twist, that is to say double twist, as shown here. This object is a pseudoscalar. The third is splay, that is to say double splay, as indicated here. This object, maybe it looks like a scalar, but when you consider that n is equivalent to -n, we really ought to think about an object that's even rather than odd in the director n. So let's take this scalar and multiply it by n itself to make this invariant mathematical object, which is a vector parallel to the local n. And then there's a fourth mode, less well known, but somewhat related to saddle splay. That is the remaining director deformation, which looks like this. Okay, so this is a director deformation which is outwards in one direction, inwards in the orthogonal direction. So it has a shape kind of like this tetrahedron. This can be characterized by a symmetric traceless tensor in the plane perpendicular to the local n. So it looks like a rank 2 tensor, but then you say, oh no, this is odd in n. I really need something even in n so that it'll be invariant under this symmetry. So let's multiply it by n again, same as we did with splay. And so that makes a third rank tensor to characterize this kind of director deformation. All right, so now in terms of those 4 normal modes, the Oseen-Frank free energy can be written like this, okay? Something times splay squared, something times twist squared, something times bend squared, something times this delta squared. Okay, so it's a sum of squares as well an elastic free energy ought to be. Okay, that is step 1. Step 2 in this ideology is to notice that each director deformation can induce some extra molecular order in the nematic phase. So for bend and splay, this is just the flexoelectric effect, as you all know very well. So if you start with a uniaxial pneumatic phase and you apply a bend, you induce a little bit of polarization perpendicular to the director. So it has the same symmetry as the bend. Likewise, if you apply some splay, you induce a little bit of polarization parallel to the director. So the same symmetry as the splay. Okay, so this is well known for flexoelectricity. For the other two modes, the twist and the delta mode, we can kind of generalize the concept of flexoelectricity. So if we start with some random distribution of chiral conformers and apply a twist, we could get a biased distribution, more right-handed than left-handed, for example. Okay, so that makes a pseudo-scalar order in the material, same symmetry as the twist. And likewise, if you think about tetrahedral objects like this one, if you start with a uniaxial pneumatic phase of these kinds of objects and you apply the delta deformation, then you get a biased distribution. You get orientational order in which way these axes are lined up. So that is some octopolar order inside the pneumatic phase. Okay, that's step two. Step three is to do step two in reverse. Okay, we notice that any of these kinds of extra molecular order might form spontaneously. If they do form spontaneously, then each of them would induce some director deformation. Okay, so a phase with pneumatic order plus a little bit of extra order. I'll call that an n plus epsilon phase. It has a little bit of one of the other kinds of molecular order, and it makes an ideal local structure with some director deformation. Okay, so if you have a little bit of perpendicular polar order, the liquid crystal wants to have some bend. If you have a little bit of parallel polar order, the liquid crystal wants to have some splay. If you have some chiral order, the liquid crystal wants to have some twist, i.e. double twist. And if you have a little bit of octopolar order, the liquid crystal wants to have some of this delta deformation. So that's what the liquid crystal wants. So now the question we have to ask is, it wants it, but can it get it? Is there a director field with the ideal bend, splay, twist, and delta? Not just at one position, but everywhere in space. The answer to that question is, in general, no. That is the phenomenon of geometric frustration, that there's an ideal local structure which cannot extend to fill up space. Okay, so there's a whole mathematical story here, but I only have time to mention one highlight in some work from Epifanio Virga. He pointed out that in three-dimensional Euclidean flat space, only certain combinations of director deformations are possible, either twist and delta or bend, twist, and delta. That's all. Nothing else can fill up space. So the liquid crystal has a problem. It wants to have a certain set of bend, twist, splay, and delta, but it can't. So what can it do to minimize its free energy? Well, in general, there are two possibilities. One is it can fill up space with some allowed combination of deformation modes, the mode that it wants plus some other mode that costs free energy. Alternatively, it can break up space into domains of the favored mode separated by domain walls or defects. Both of those things can happen. Let me demonstrate. Okay, so what is possible? First, let's consider a liquid crystal that is chiral, okay? It has a modulation driven by chirality, so it wants to have twist, okay? but it can't fill up space with pure double twist. So what can it do? One possibility, of course, is to make a cholesteric phase with a director field like this. This is a phase that has no splay, no bend. It does have twist, and it also has this delta mode. So the liquid crystal has the splay, excuse me, the twist that it likes, and it accepts some of the delta mode that it doesn't like. Alternatively, it can make a blue phase. That is, it can make cylinders with the ideal double twist, approximately pure, but they have to be separated by disclination lines. So which is better? Well, in the cholesteric phase, it gets twist everywhere, but it has to accept the unfavorable delta mode. In a blue phase, it gets twist everywhere, but it has to accept the unfavorable disclination cores. So which is worse? Well, it depends on the disclination core energy versus the energy cost of the delta mode, which is K24. So if the disclination core energy is high, it makes a cholesteric phase. If the K24 is high, it makes a blue phase. Okay, so that's a way of thinking about this classic problem in liquid crystal physics. What about if you have a material with perpendicular polar order? Okay. Well, one possibility is that, well, I should say the liquid crystal wants to make bend, right? That's what has a negative free energy. Okay. One possibility for what the liquid crystal can do then is to make a twist bend nematic phase like this. Okay. That has bend. That's the good news. The bad news is it also has twist and delta. That makes an unfavorable free energy. But this is a reasonable compromise. It makes a twist bend nematic phase, which of course has been studied by many people in this conference. Okay. Alternatively, the liquid crystal can make regions of bend separated by domain walls. And so one example of that would be this splay bend nematic phase, where there's a nice bend region and then a wall, and a bend region and then a wall, and so forth. Or it could be a more complicated kind of structure where there's, say, a hexagonal lattice of bend regions that are separated by walls. Okay. So that's a liquid crystal with perpendicular polar order. What if there's parallel polar order, parallel to the director, so that the liquid crystal tends to have splay, right? It wants splay. Now, there isn't any allowed uniform combination of modes that includes splay. So this possibility number one doesn't work. But it can still do the possibility number two. That is, it can make splay regions separated by domain walls. So there could be a one-dimensional splay nematic phase like this, okay, with a splay domain and then a wall and another domain and another wall and so forth. That could be arranged in this one-dimensional style. It could be arranged in this two-dimensional fashion with a checkerboard lattice of splay up and splay down. Or it could be arranged in an even more complicated three-dimensionally modulated way like this. Okay. And then finally, just for the sake of completeness, let's suppose that a liquid crystal has octopolar order. That is, it has orientational order of these tetrahedral kinds of objects, so that it wants to have a delta mode, okay? Can't have pure delta mode. What can it do? Well, it could have a uniform combination of delta mode and twist. So to make a spontaneous cholesteric phase, which could be either right-handed or left-handed, as in these images, or alternatively, it could make regions of the delta mode separated by domain walls. So that would look just like a 1D or 2D splay nematic phase. Okay, so this one-dimensional modulation or this 2D checkerboard-like modulation. And this is what's discussed in the poster here of my Brazilian student, Michele Rosetta. Okay, so these are stories about a nematic phase with a little bit of extra order, any of these four forms. There are related stories for a smectic phase with a little bit of extra order. I don't have much time, so let me just mention a few pictures briefly, okay? If you have a smectic phase, there are extra constraints because of the layers. So there's even more geometric frustration. So if you have a smectic phase that wants to have twist, one possibility would be a twist grain boundary phase, right? So that it has the twist concentrated in these walls. Another possibility would be the helical nanofilaments. This is the model of Sabeta Matsumoto et al. So that it has twist, but it sacrifices the smectic A requirement of a director normal to the layers. What if you have a liquid crystal with intrinsic octopolar order so that it wants to have the delta mode? What can it do then? Well, that could make a different model for helical nanofilaments, okay? A model more like the original model of the experimental group of Huff et al., okay? Where it has a delta mode right along the central axis, and then it has to mix in other stuff as you go away from the central axis. What about if there's parallel polar order? Well, then you could get this lattice of onions that is micelle-like objects, like the concept of spontaneous curvature in membrane biophysics. And finally, if the liquid crystal, a smectic liquid crystal, has perpendicular polar order, no one's ever thought about that very much, but de Gennes thought about that a little bit a long time ago. And he proposed this thing with a lattice of edge dislocations. Maybe that could happen. It's kind of a TGB-like phase. All right, I'm out of time. So let me wrap up with the main conclusions of this study. That is this great big table here, that there are 4 types of deformations in a liquid crystal director field. Each of these is a different type of mathematical object. Each of these couples with a kind of molecular order, so that there could be a phase that has a spontaneous tendency towards one of these deformation modes. However, because of geometric frustration, it can't achieve exactly what it wants. It has to do something more complicated with a mixture of modes or with domains separated by defects or domain walls. And that, I think, makes a pretty nice way to think about the rich variety of modulated phases, all the phenomena that we study in this field of liquid crystals. So with that, I'll close. If anyone's interested, I'll point to these articles that I have up on archive. And I thank you very much.
Thank you, Jonathan. As a theoretician, I enjoyed every single second of your talk. But the auditorium questions, please.
Thank you, Jonathan, for a very nice talk. If you have modulated phases, then locally they become also biaxial in some. So it gets more complicated, doesn't it?
Yes, yes, it does. The delta mode there that I talked about is in itself sort of biaxial, right? In that it has a splay outward in certain directions and inward in certain directions, right? Going out like this and in like this. So that's similar to biaxial, but I would call it maybe tetrahedral, right? Because it's a little bit different. Now, there's a remaining type of molecular order that I didn't talk about here, which is regular biaxial nematic order. That is the order of rectangular blocks. That type of order could also be present. However, it doesn't couple directly to any of these 4 deformation modes. And so a biaxial nematic phase does not have a spontaneous tendency for a director deformation, right? Unlike something with one of these other types of order, polar order or chiral order or octopolar order. And so that can be present also without inducing a modulation. So maybe that's at least a partial answer to your question.
Yeah, thank you. There is a question from the
online. Yeah, please, Shi-chan, can you unmute yourself and go ahead?
Yeah, hi. Can you hear me? So my question is just like, thanks for the great talk. My question is about like, for like long range interaction, like dipole-dipole interactions, like you have a splay, you have a spatial charge that can interact with other spatial charge. For this kind of long range interaction, could that be incorporated in your like model?
I couldn't hear you very well because of the audio feedback. I'm sorry.
Sorry,
I think the question had to do with the possibility of long-range interactions, right? And how long-range interactions could be incorporated. It's a great question. I'm not sure quite what the answer is. I'm not sure. I think the point is that the tendency towards a modulated phase is a local tendency, right? The effect that I'm identifying, this converse flexoelectric effect, if you will, is a local tendency. Then the geometric frustration is a more long-range constraint. I think the question was, what if there are other long-range effects, right? What if there is some other long-range interaction that would certainly have to be considered together with the geometric frustration? Okay, and so that would provide further constraints on what types of phases could form. I guess that's the best I can do. If I misunderstood, please send me an email and let's discuss it further.
Yeah, thank you very much. Sorry for the sound effect. Yeah.
So I think that at this point we have to stop discussion, and I would like to thank Jonathan for this talk, and please.